Radiologic technologists need to understand how magnetism works to better understand our equipment. There are three different ways we can find magnetic fields. One is through naturally occurring materials, two are through artificially induced magnets, and three are through electromagnets. Examples of naturally occurring magnetic fields are literally the Earth and materials within the Earth, such as this iode stone. We can create artificial magnetic fields, such as this bar magnet or refrigerator magnets. Electricity running through a wire produces a magnetic field. The intensity of that magnetic field is proportional to the electrical current. Remember, we measure current in amps, so the higher the amps, the stronger the magnetic field. Magnets consist of two poles, a north pole and a south pole. We call this a dipole. Magnetic fields leave the north pole and magnetic fields enter the south pole. There are three different magnetic materials that are important for us in radiography. They are ferromagnetic, diamagnetic, and paramagnetic. A ferromagnetic material is any material that does not become a magnet until it is in the presence of a magnetic field. Once strongly magnetized, ferromagnetic material act like a typical magnet, with unlike poles attracting and like poles repelling. For example, this iron nail is considered a ferromagnetic material. If you find a nail in your home and touch a paper clip, nothing will happen. However, if you attach a magnet to the end of the nail, then that nail will become magnetized. With that magnetized nail, you'll be able to pick up a paper clip. And why is that? Well, before the nail was magnetized, the domains were not aligned. And what are domains? If we zoom into the nail, we'll see a crystalline structure similar to this. These are all individual domains. Here we have a stylized version of those domains. The direction of magnetic fields in this ferromagnetic material are not aligned. However, in the presence of a strong magnet, the lines of magnetic field align with each other, thus making the ferromagnetic material strongly magnetized. Another way to visualize this is with arrows. Notice again that the direction of magnetic fields in this ferromagnetic material are not aligned. However, in the presence of a strong magnet, the lines of magnetic field align with each other, thus making the ferromagnetic material strongly magnetized. Now, paramagnetic material is different than the regular magnetism you're used to. Paramagnetic material is weakly attracted to both sides of a magnetic field. Aluminum is an example of this. However, radiologic technologists commonly use a different paramagnetic material. Radiologic technologists use the paramagnetic contrast media gadolinium in some of our MRI exams. And again, paramagnetic material is weakly attracted to both sides of a magnetic pole. Finally, diamagnetic material is also different than the regular magnetism you're used to. Diamagnetic material weakly repels both sides of a magnetic field. Bismuth is an example of this. Water is also diamagnetic. That's how we can levitate frogs. More on that later. We now know where magnetic material comes from and the different types of magnetic material. But what's happening on an atomic level to produce magnetic fields? The first way magnetic fields are produced on the atomic level is by electrons spinning on a stationary axis. Here, the golf ball represents an electron. When an electron is spinning on a stationary axis, the magnetic field is created on the axis of movement. The second way magnetic fields are produced on the atomic level is by electrons moving forward on an axis. Again, the golf ball represents an electron. When the electron is moving forward along an axis, the magnetic field is perpendicular to that axis. Interestingly enough, we can determine in which direction the magnetic field is moving by using the right-hand rule. Using your right hand, point your thumb in the direction of the electrical charge. Your fingers will curl in the direction of the magnetic field. In this example, the magnetic field moves toward you underneath the axis and away from you above the axis. The SI unit for measuring magnetic field strength is the Tesla. The magnetic field strength at the North Pole is about 100 microteslas, but only 50 microteslas at the equator. A typical refrigerator magnet is about 5 millitesla. However, in MRI, our MR machines can range from 1.5 to 10.5 teslas. There are even experimental MRI machines that can reach 17 teslas. At 17 Tesla, you can also theoretically levitate a frog. How can a frog levitate using a magnet? Well, remember when we said water is a diamagnetic material, meaning it weakly repels both poles of a magnet? A frog is mostly water, so using strong enough magnets, we can theoretically levitate a frog.